And after this short presentation, I am very pleased to now to introduce the other 5 open source software solutions, and not only their outcomes, but also the faces behind these projects. The first team, which is with us, is the one formed by Roshni Biswas and Anurag Saha Roy. The project, named DeepGEFF, has made use of deep learning techniques to increase wildfire prediction coverage on timescale. I hand over Roshni. And you are ready?
Hello, my name is Roshni, and I'm here to talk about DeepGEFF, a project that Anurag and I have been working on over the last 6 months or so throughout the summer and duration of ESoC to better predict wildfires. This project is called DeepGEFF, and we started working on this because, as we know, in 2020 we've been seeing a lot more wildfires. And due to the degradation of the climate, wildfires, although a natural disaster, they are getting more and more frequent, more and more dangerous. So this is why we decided to kind of take hit at how wildfires can be better predicted using the latest developments of technology in machine learning and artificial intelligence. So this project is part of Stream 2. And we were, as you can see, Anurag and I, Tejasvi also worked on this, and Claudia and Tianran were our mentors from ECMWF. So yeah, let me give you a bit of background on DeepGEFF and what exactly are wildfires, although I'm sure we all know. Wildfires, although categorized as a natural disaster, these are large fires that grow, that burn and spread uncontrollably in areas like vegetation, forests, grasslands. And these cause a lot of destruction for people, for the environment. So it is very important that we look closely into how a fire starts and why it persists in a particular location. So that is kind of the analysis that we worked on to better quantify where a fire is going to ignite and what are the pre-existing conditions that help the fire to persist in that location. So as you can see on this map, this has a plot of an index called the Fire Weather Index, and it's a meteorological based index that's used by fire danger teams all around the world to kind of quantify fire danger. So there's a color scheme on the right side. The more dangerous regions are marked in black, and the lesser ones are down below in green. And this index is calculated using weather conditions. These are called forcings variables. Particularly these 4 variables that we can see over here: air temperature, humidity, wind speed, and rainfall. And these are calculated either ground measured from the ground or remotely sensed. The various variables that we'll be using are all geospatial products, either sensed by satellites or taken from the ground. So these are mostly taken from the ground or at a particular height over the surface of the Earth at a time. So these are all taken at 12 p.m. local time. And there's a underlying calculation that happens to calculate the fire weather index from these forcings variables. So this particular scheme has been used for decades, over the last like 3 or 4 decades, initially developed and then has been kind of taken up by the Canadian government, the French government, the US government, various adaptations of the same calculation of FWI. So what does FW actually mean? I've been talking about all these numbers and all the calculations. So if we had to pictorially represent a fire with kind of like a low FWI value, say 15, would look less dangerous, as you can see on the right side, and then a more dangerous fire, FWI value 24, looks far more dangerous. Now, FWI can vary quite a bit. It goes from, say, a null value to something that's like over 100, depending on which part of the world you are. It's a unitless constant, but the classification scheme varies from region to region. Now, apart from FWI, FRP is another variable that we spent the later half of the project focusing on. FRP is also another index, very similar to FWI. It is an observed value, though, in the way that it differs, and it is basically a measure of also a measure of how dangerous the fire is, but more on it represents like how much energy is radiated from the fire during the process. So this FRP is used as a proxy for figuring out, what are the combustion rates, what is the fuel behind the biomass, and what causes kind of fire to spread. So that is the kind of derivative that we are looking at from FRP. So as you can see in this image, this is also a plot of FRP where the values go from 0 to a very high 22,000. And we can see that the grid cells that are ignited are marked in the particular color that falls into the scheme. So here we can see actively burning fires detected in around June 2015. And this is, as I said, an observed value, so it's directed by the MODIS satellite. So now our machine learning take on this project was to look at all these underlying conditions, feed it into a machine learning model. You can treat it as a black box model, and then make a prediction on the FWI value or the FRP value, and see how many days in advance we're kind of able to predict that a fire is going to occur, a fire is going to occur, and how dangerous it's going to be. So fire occurrence is a bigger challenge because statistics have said that like 10 to 15% fires are naturally occurring, and most fires are ignited due to either human intervention. So they are far more difficult to predict. But the fires that occur due to natural conditions are just based on the weather forcings variable. So if there's the environment needed, the temperature, rainfall, humidity, and the biomass needed to kind of fuel the fire, then a fire might as well occur and persist. So that is how we kind of approach this problem. This is the life cycle of a typical machine learning problem. So we looked at the data, we found what are the patterns in the data, we trained a machine learning algorithm. In this case, we picked a UNet style algorithm. We built the model, trained on whatever data we found, like over the past 1 or 2 years, and then built a model that's going to make essentially a prediction of, say, the next week or the next month on what are the FWI values in the region, or we make global predictions. So you can look at one particular region and figure out what are the FWI FRP values. So our goals for this, if I had to kind of list them out, they would firstly to kind of reproduce the numerical modeling that was already existing in the models that we had over the past decades, but kind of reproduce them not using a numerical approach, but more using a machine learning approach, and then improve the quality of the predictions we have on either on the basis of accuracy level or on time scale. We were able to do both over the course of the project, and currently the time scales would only be up to, say, 7 to 10 days, but now we are able to make longer predictions. And we also study the correlation of various additional variables to fire danger. So initially for FWI calculation, I talked about how only the 4 forcings variables are used, but we have looked into what newer variables that are now available detected by various satellites that are more recently out there can be added to kind of improve these predictions. And lastly, we approached how to model fire spread dynamics. So this is kind of sets the stage for the project, and Anurag will talk about the results that we achieved, which are very exciting. So I'll hand it over to Anurag right now.
Thanks, Roshni. So I'll be going over the results, and we'll be having different kind of results as we progress down the presentation. So to start off, the good parts, the good results, the more successful parts of the project. One part of the prediction was to make fire weather index prediction at par or better than what we already have using numerical modeling. And what you see on the slide here is the deep learning architecture that we used for obtaining this prediction. And our prediction accuracies were at par or better than the numerical modeling. And this is for the typical 10-day prediction that is currently practiced in the numerical models. So when I say 10-day prediction, I mean that if I start today and I look up the online or any other FWI prediction scheme, I get the prediction for the next 10 days for any particular region, what is the expected fire weather index for that region. And we reproduce that using the machine learning model. And as you see here, the accuracies start from above 90% for day 1 or day 0, as we like to call it, and go down till 80%. So that was sort of one of our targets which we proposed in the initial ESoC proposal application. And we are quite happy that we were able to reach the target of ensuring 80% accuracy, global accuracy in predictions until the 10th day. What you see beneath is that on the extreme left, that is how the actual data looks. So when Roshni was mentioning that we use temperature, we use rainfall, we use humidity, when you plot that data on the global map, that's how the leftmost block looks like. And what you have in the center is the deep learning architecture. And then as an output of this deep learning model, you get this prediction of FWI values. Now, on a more visual demonstration, this is how it actually looks. So on the left is what you have, an observed FWI. Well, it's kind of a stretch calling it an observed FWI. It's more like FWI reanalysis. And on right, what you have is the prediction of the machine learning model that we have developed. And as you can see, of course, it's not perfect. And we would be quite exaggerating if we said it were perfect, but it's good. And it's quite accurate. And what makes us happy is that the model errs on the side of caution, that it would rather predict that the FWI values are higher than they are lower, maybe plus minus 5 or 10. But what this means or how this helps is that you would always be extra cautious from the FWI values, and you would have less chance of a reporting or a prediction that is much, much lower than what the actual FWI value turns out to be. Now, the second part, or one of the extensions of the project, involved studying the effects of different additional variables on prediction of FWI. Now, when I say additional variables, what I mean is that other than the 4 variables, temperature, rainfall, humidity, and wind speed, we introduced additional variables into the machine learning model, and we explored how that improves the accuracy, how that improves the learning. So there are a few reasons why one would want to introduce additional variables. Firstly, does it improve the accuracy? Secondly, does it make my training much faster? So instead of training for 100 epochs, can I just train for 30 epochs and get as well results? Or thirdly, can I use less data? Instead of training for 1 year, can I just train for, I don't know, 3 months, 4 months and get comparable accuracies? So these are the kind of motivations that we had when we started to introduce additional variables. And one by one, I'll go through them and tell you what kind of conclusions we made when we introduced these variables. So firstly, skin temperature. Land skin temperature or skin temperature is essentially a measure of the temperature of the Earth's surface. And when we introduced this as an additional variable, we saw that the global accuracy that we achieved was 68% by training only 30 epochs and on 4 months of data. To give a comparison, all the numbers that we're reporting until now of 90% plus, 80% plus accuracy, those were done training for 100 epochs for 1 whole year of data. So this is definitely progress in the right direction. That makes us happy that yes, this introduction of this variable makes training faster. We can train on less data and still get comparable accuracies. Next up is soil moisture. So soil moisture or volumetric soil water is a measure of the moisture content in the soil. And once again, what we see is that if we include soil moisture, we are able to obtain accuracies in the 65 to 70% regime with very few epochs and very little data. So that's the important part. And why it is important is because this data is huge. To give an impression, we were working with 1 TB of data, 1 terabyte or 1000 gigabytes of data for the whole year. And typically it would take a couple of days to train the whole model on that data for 1 whole year. So if we can do less number of epochs, if we can do smaller data sets and still get good results, that's great. We want that. We want that sort of efficiency. The next variable that we studied was vegetation. Of course, I think it's quite intuitive to feel that vegetation would be a natural factor that should be included because, well, you can't burn anything if you don't have trees to burn, right? So we, of course, thought similarly, and we included leaf area index as a product for this. But surprisingly, we did not have any strong correlations or improvement in the FWI predictions. And our understanding is that this is because green leaves as such, or green moist leaves, do not burn as well as dried leaves or cured vegetation. And this particular measure of vegetation that we are using is a measure of the green vegetation. So even though presence of vegetation definitely has a correlation with the fire weather index, or has a correlation with the occurrence of a fire, it's important to note that there will be a time lag. So if I note that there is vegetation today, maybe 60 days from now, when this vegetation has been cured, that is when the fire weather index will go up, which is why we did not notice an immediate improvement in the predictions. Now, we also wanted to increase the time scales, and this was quite a happy result for us, that we trained on 6 months of data for 30 epochs, and we noticed that the prediction accuracies stay quite consistent. So previously we were using 4 days of data on the input side and producing predictions for 10 days. Here we used 7 days of data on the input side and produced predictions for 21 days. And we see that even up till the 21st day, the prediction accuracy stays above 70%, which is very promising to us. And we will continue work on this direction to, let's say, train on the whole year data set and train for even more epochs. And hopefully we can get comparable accuracies to the current 10-day prediction timescale. Now, in the spirit of open science and open code, what are the not so good results? Well, not so good results, more like what are the challenges? So the numbers that we reported so far look great, right? And they are great. We do feel very lucky to have been working on a project that turned out quite well. But it's also important to understand the nuances behind these metrics. And it's very easy to get carried away with top level metrics, but we were lucky to have mentors who are well versed in this domain, who are well versed in this kind of problems. And they were quite prompt to warn us that it's not just okay to understand the prediction accuracies for the global case or for all values, but we also need to understand how the prediction accuracy is when we are looking at very high FWI values. And this is because high FWI values are often of more interest to us. So this is what we show here, that even though the accuracies are quite great for 10 days of prediction, as we move into higher FWI values, we see that the prediction accuracies take a hit. And of course, this made us a bit worried. So we went back and we wanted to benchmark that how does this perform with the current baseline. So the current baseline is the numerical prediction model, which has been there for a couple of decades now. And that's what is used in the current predictions. And we are quite happy that even though the accuracies of the machine learning model seem to deteriorate over time for higher FWI values, they are still better than the numerical prediction. So what you see in this plot are the line plots. The line plots are the numerical prediction, whereas all the bar plots, they are the predictions from the machine learning model. And as you can see, they are almost always either at the same level as the baseline, or the machine learning model does better. So again, it's a promising direction, and it's good that we noted that the accuracies need to be presented in this form of divided manner, because this also gives us a better understanding of where we can improve the machine learning model. And this is also why we undertook different steps like class balance loss or pre-processing of the data, and how they improve the machine learning model in predicting values which are much fewer in the data set. So I think it's important that when we work in an open source project, when we work in open science, that we highlight and present the bad results as much as we celebrate the good results. So it's important that we highlight what went wrong, what we could not do, what did not work out, and that is what this part of the talk focuses on. So firstly, fire radiative power. So this is a plot of the fire radiative power, and as you can see, it's a very, very long-tailed data, with much of it being skewed in the 0 to 20 regime, with very few data points above 60. And this posed as a huge problem for us, because even after trying out different data transformation techniques, we realized that the machine learning model will almost always perform very poorly on making predictions for higher FRP values. And that continued to be the case. And we have still not figured out a very straightforward approach to how we could tackle this. We have thought of dividing the whole data into two halves, something like below 20 and above 20, and that could possibly be an approach, but yeah, nothing very promising so far. Next up, so then on further discussion with our mentors, and we were very lucky to have such well-informed mentors who could constantly guide us, we decided to divide this problem into two parts. The first part is fire ignition. So as Roshni mentioned, fire radiative power is an observed value of how much energy is being emitted from a fire. And when you take a look at the data and you're trying to, let's say, predict the fire radiative power for tomorrow, there could be two cases. One, there is an ongoing fire and you're trying to predict the fire radiative power of this fire for tomorrow. The second and the more interesting one is where you don't have a fire today and you are trying to predict the fire radiative power for that tomorrow. Now, I think it's becoming clear why that latter problem is quite an interesting challenge, quite an uphill challenge, and that is the challenge of fire ignition. So fire ignition is either due to human activity or due to lightning in most cases, and predicting fire ignition is a whole different challenge. We realize that including that as a part of fire radiative power prediction would be quite a humongous task, which is why we're exploring data sets that help integrate human activity and lightning into that prediction. The second part is modeling fire dynamics, that we want to look at how does the fire spread when you have an ongoing fire. And there are different factors that affect it. There is burnable biomass, there is presence of fire in the adjacent areas, there could be control measures like a fire line or firefighters fighting the fire, and there are also weather factors. So we're currently exploring reinforcement learning based approaches, because reinforcement learning is typically quite robust in such cases, which is why we have decided to go down that path and take a shot. And currently we are in the process of modeling the system as a reinforcement learning problem to be able to better overcome the data challenges that we previously outlined. So the key takeaways, what did we learn? What can we share? So first thing, data cleaning and pre-processing is more important and more time consuming than machine learning engineering. So both Roshni and I have worked on machine learning projects before, but definitely not of the scale that we worked on for ESoC, and definitely not such sophisticated data sets. So it was a wonderful experience in understanding how important it is to prepare the data before you start messing around with your machine learning models. Secondly, I think, which I already previously highlighted, is that metrics. Metrics are very nuanced factors, and it's important that when you report them, when you talk about these metrics, you don't get carried away by the very top level numbers, and make sure you describe what is the underlying description of those metrics. I think this is a part of a much bigger problem in machine learning right now, the understandability. And this is a part of that just getting an accuracy number is not sufficient. Thirdly, because of course this is ESoC, so it is a coding project. This is also something that we learned over the course of the project, that if you write good code that can be easily extended, that can be easily modified, that will probably be a much bigger incentive, a much bigger benefit than producing quick research outputs, because you will inevitably come back to this code and want to make extensions, want to add features, want to add enhancements. And if your code is not very extensible, you will typically end up wasting a lot more time in refactoring the code than if you had spent that extra time in the beginning and maybe been a slight slow output on the research side. And finally, of course, I think both Roshni and I felt that it's important to have fun, even when the results might not look promising, or even when they look promising. And a last call to action for everybody who's hearing us. This is the GitHub repo. Please go visit the repo. We have notebooks that explain the whole code. We have notebooks that visualize the results, that guide you through the entire process of using our code base and getting results on your own. And we are open to contributions. Please, it's an open source project, so come help us build DeepGEFF and make it an even bigger success. Thank you so much.
Thank you so much, Roshni and Anurag. It's an excellent presentation, very impressive findings. We have a comment from you, from Peter Duven. It says, great talk. You could try to work with the structural similarity index to get sharper edges in the deep learning predictions and less blur fill.
Thank you so much, Peter. Yeah, thank you, Esperanza.
Thank you very much.